So last time we talked about the boiling points of solutions and how the boiling point of a solution compares to the boiling point of the pure solvent. Let's look now at freezing point. So we'll start with this. When a solution freezes, the solute particles get in the way of the solvent particles freezing. They interfere with the ability of these solvent particles to form the necessary attractions to turn from a liquid into a solid. Consequently, the freezing point of a solution is lower than the freezing point of a pure solvent. So let's look at the formula for what's called freezing point depression. Depression because the freezing point is lowered. Does this look familiar? So this time we have Kf, freezing constant for the solvents. So same approach as what we used with boiling, with one big difference. That being when we calculate delta T, we're going to subtract that from the normal freezing point of the solvent. So remember when we were calculating boiling point, we added delta T to the normal boiling point. Now we're going to subtract delta TF from the freezing point of the solvent. So kind of like with boiling, the solid produced by a freezing solution consists only of pure solvents, and the solute particles are left behind in the solution. So let's say you take a solution of sodium chloride, stick it in the freezer. Well, over time, the water is going to freeze, but nothing happens with the salt. It's going to stay in the remaining solution. So that will have an effect on the freezing point. So let's take a look at a graph, once again, of temperature versus time. And this time we're going to show what happens as you remove energy from, we'll start with the pure solvent at a constant rate. And so we get something like this. And then as that substance freezes, we see that. So again, remember, during a phase change, the temperature of a substance does not change. All right, so let's do the same thing this time with our solution. So here, let's make a key. Oh, we have a key. We have solvents. Here's our solution. So again, we see that the substances freeze at different temperatures. And again, kind of like what we talked about with boiling yesterday, during the freezing process, since the solute does not freeze along with the solvent, that solution as it freezes will become more and more concentrated. And as we saw with boiling points, as concentration increases, as M goes up, so does delta T, our difference, again, between the freezing point of the solution and that of the pure solvent. Once again, we'll do it from here. So here's the freezing point of the solvent by itself. And right here where, reaches kind of a initial minimum temperature. So from here to here, that is our delta T, the difference between the freezing point of the solvent and that of the solution. Take a look on page 527, 21.5. We have a phase diagram, shows both for a pure solvent and a mixture. Notice that the mixture has both a higher boiling point and a lower freezing point. So it's not higher for both. Higher boiling point, but lower freezing point. Take a look at the example. Last time we did boiling point. This time let's calculate the freezing point of this solution. So I already have the molality there. So let's plug that in, 1.01 molal. This time we're going to use the freezing constant for water. And if you look back at the table, the value for the freezing constant of water is 1.853 degrees Celsius per molal. Let's punch this up separately, and then I'll show you what to do with that. Pause the video now. So once again, this is delta T. This is not the answer to the question. The question was not how much does the freezing point change by, but what is the freezing point of the solution? So this time we are going to take the freezing point of the solvent by itself minus delta T, and it has to be in that order. Can't be the other way around, otherwise we're going to get a positive value, which doesn't make sense. So the freezing point of this solution is negative 1.87 degrees Celsius. All right, let's go ahead and try this one. Again, we are not doing we're not doing boiling point. We're going to do freezing points. So we got to change this, and we got to change that, and change our answer. Go ahead and pause and do that now, please. All right, here we go, negative 6.43 degrees Celsius for that one. There's our setup. And let's do one more again, just so we don't get so used to using water all the time. Again, our solvent is nitrobenzene. Calculate the freezing point. Go ahead and pause the video now. All right, be careful with the acidic figs. We got 2 digits after the decimal, 1 digit after the decimal, so our answer will have 1 digit after the decimal, freezing point being negative 4.8 degrees Celsius. All right, same thing with freezing point as boiling points of solutions containing ionic solutes. So we'll change our equation up here a little bit and change our constants. And then change how we arrive at our final answer. I'm going to let you do this. So go ahead and finish this problem, pause the video. So again, Van 't Hoff factor is 2. Plug in our Kf, our solvents. We get a freezing point depression of 5.15 degrees Celsius. Subtract that from the normal freezing point of water. We get negative 5.15 degrees Celsius for the freezing point. All right, so let's do freezing point this time for this solution. Go ahead and set that up, pause the video, get your answer. All right, so we get this time negative 9.60 degrees Celsius. All right, so that concludes this lesson. So hopefully if you understand how to do boiling points of solution calculations, that freezing point is not too bad. This time though, just remember we are not adding, we are subtracting. All right, thanks for watching.